Hey everyone, welcome back. This is lesson 4 in our unit 9, Kinetics and Equilibrium unit. So in the last video, we covered potential energy diagrams, and in this video, we're going to cover what entropy is. So my first question to you is, looking at this GIF of a dog, you see him or her pulling his or her sled up the hill, and then getting in it and going down. And so which part of that is spontaneous and which part of it is non-spontaneous? And so if we're talking about this, the spontaneous part is the going downhill. So once the dog is going down, no more energy is needed to be put in, but that non-spontaneous part, that is going up the hill. And so the difference between non-spontaneous and spontaneous is spontaneous means something can proceed without really that need of that outside energy. So if we think of, and these are generally exothermic reactions. So if we think of an exothermic reaction potential energy diagram, yes, all equations need that little bit of activation energy, but once it's going, it can continue to go without a problem. And so you don't really need that outside source of energy. And so once that dog was going down the hill, it just kept going. Non-spontaneous, on the other hand, needs that input of energy. And so if you have your endothermic reaction, you need a lot of energy to get that started. And it doesn't really happen on its own. It needs that input of energy. And so when we're talking about spontaneous reactions, they happen generally when there's less energy. And so remember, enthalpy is that heat energy, that heat, H I like to say is heat, that heat energy. So that lower energy, and that's why these exothermic reactions are favored. It also happens when you have this great randomness or disorder. And so this randomness and disorder brings us to a new vocabulary term, which is entropy. And so entropy is the measure or the disorder or randomness in a system. And so a system is a fancy word just for area. And so generally speaking, nature favors greater entropy. So it favors more randomness, more disorder. And so when we talked about this word the other day, I like to use that capital H to remind myself that it is heat energy. And when we're talking about entropy, that R is randomness. So that's how I keep them separate in my head. But nature favors this greater entropy, this big unorganized mess. And it also favors, based on what we wrote on the other slide, lower energy. So nature favors great entropy and lower energy, kind of like that stereotypical teenager. Very low energy, very messy. That is what the universe and nature favors. And so if we're looking at different phases of matter, solids are very, very highly organized. So you have low entropy and high organization. And if we look at our gases, we have high entropy and low organization. And so as you go from solid to liquid, from liquid to gas, you become more and more random. And so that's why as you go this way, entropy increases. And so here you have two pictures. Which picture has higher entropy? You guys should be thinking the before. It is quite the mess. In this before-after picture, which has higher entropy, again, you should be thinking the before, quite a mess, but becomes neater. And so if we look at the desk's picture, this might be easier to kind of visualize if you have a desk. It's very easy for your desk to become unorganized, or even your laundry basket. As time goes on, it becomes more and more organized, more and more disorganized and messy. But if you wanted to neaten that up, you yourself need to put in energy to neaten it up. So if you just keep dumping papers on your desk whenever you walk in, it just becomes more and more unorganized. But then you have to actively neaten everything up, and that takes energy. So this happens spontaneously, that mess, and cleaning it up is non-spontaneous. Okay, so if we want to increase entropy, you want to increase that randomness, first thing you can do is have more molecules in a reaction. So if you think of babysitting, if you are in charge of babysitting one kid, keeping one kid under control is easier. And then if you have two kids and they're running in opposite directions, that's more chaos and more disorder. If you have three kids, that's even more. So the increase of molecules in a reaction, the more unorganized or the more randomness that happens, the higher the entropy. If you increase your temperature, remember temperature is average kinetic energy. And so when you increase that temperature, you're increasing your average kinetic energy and you're increasing the speed of the molecules. And so faster moving particles become way more unorganized. And then this is just our phase changes. Remember, from solid to liquid, you're becoming more unorganized, and from liquid to gas. So gas, remember, is the most random, least organized thing. Just to kind of go back with our number of molecules example. Here you have one compound, NaCl, it's combined. And then you're ending with two other pieces. So one thing and two things become more difficult. You also have these phase changes, these phases of matter. A solid is pretty organized. Then you have aqueous, which means you have these two things in water. So you have your Na plus just kind of floating around in the water. You have your Cl minus just kind of floating in the water. Oops. And then you have your water molecules just kind of floating there. So that becomes much more messy and disorganized rather than a cube of NaCl. So this picture right here shows it. It shows, a kid making a mess and blaming it on science. A true, accurate reasoning, but probably people at home will not appreciate you saying, "Oh, hey, clean your room," and you saying, "Nah, entropy wants this. The universe wants a randomness." Not the response your family will be wanting. Anyway, let's jump into a few questions. You have given this balanced equation, describe the change. And so we have to figure out if it's endo or exothermic, and then what happens to the entropy. And so you'll notice we have energy as a reactant. And so if you have energy as a reactant, that means it is absorbed, which means it is endothermic. So we can get rid of C and D. And then we have our phases, a solid to a gas. We're becoming more random. So your entropy increases, making our answer B. Number 2, the entropy of a sample of H2O increases as the sample changes from. Remember, as you go from solid to liquid or liquid to gas, your entropy increases. And if we go backwards, your entropy decreases. So, with that being said, gas to liquid is going backwards, gas to solid is going backwards, liquids to gas is going forwards in, terms of that, and liquid to solid is backwards, so that makes C our answer. Again, gas is the most unorganized, has the highest entropy. Number 3, which has the least entropy, so we want the most organized. And so we have different phases of matter, so we're going to want a solid, and we have different temperatures. You're going to want a low temperature. So solids and low temperatures are the most organized, so the least entropy, and that makes it answer choice A. And lastly, number 4, in terms of energy and entropy, systems in nature tend to undergo changes towards. This is when you should think of the stereotypical lazy teenager. You have low energy, and you're kind of messy, so that's high entropy, low energy, making it C. So that is it. Next time, we will cover rates of reaction. On that note, have